My name is Joel Hahm. I'm a senior engineer with Contech Engineered Solutions. I deal mostly with flexible buried bridges, helping develop projects internally and also with engineers and contractors. In addition to that, I'm involved a lot with AASHTO and ASTM and other committees with helping to develop and improve standards. And I'm also chair of the TRB subcommittee on buried bridges, which is a subcommittee of the, I think with the restructuring, it's called Buried Structures and Soil Structure Interaction. And I'm also the starting left tackle for the Short Span Steel Bridge Alliance football team. So today I'm talking about, they asked me to talk about buried bridge design innovations. Something real quick, maybe a real quick review for people who don't know that the design standards for buried bridges are included in Section 12 in the AASHTO LRFD. More specifically, what I'm going to show you today is in 12.8.9, which is deep corrugated structural plate. These structures are not proprietary. Everything that anybody needs for design, manufacturing, and construction is available in AASHTO and ASTM standards. So there's nothing preventing any agency from specifying this specific material. It's just up to everybody whether they want to invest in being able to learn how to design it and manufacture it. The design of these structures requires finite element analysis, which includes inputs for foundation and site soils, backfill, the structure shape itself, along with the material properties and loading conditions. In terms of design innovation, once I started thinking about that, I realized that really that happens on almost every project. Most of the innovations are driven by developing a project-specific solution, which usually involves a custom geometry to meet specific clearance requirements and site limitations, and then also optimizing that geometry and how you approach the analysis to best fit the site and the loading conditions. Another area where a lot of innovation, even more so than on the design side, tends to come in is on the construction side. Usually after the design is completed, there may be specific challenges regarding construction the contractor deals with. So that's what I'm going to focus on today with the innovation I'm going to show you, which is dealing with modular construction of buried bridges. I think everyone involved or who's been exposed to the Short Span Steel Bridge Alliance understands that with the beam bridge side, but it's also starting to become more common with buried bridges too. So what am I talking about with modular construction? Well, for these structures, they're usually larger span structures. It involves pre-assembly of large sections of the structure, transporting it or lifting it onto the foundation, and then connecting those modules to each other after it's in place. There are a couple of different reasons that somebody might want to look at construction this way. One is that there's limited space for material and staging equipment. So usually when you're building these, you want a place to kind of stage the plates so you can lift them in a convenient location to efficiently set them on the foundation and add them to the structure. A lot of sites just don't have the space for that, or the equipment that you need to build it, the site is too rough or on a slope or in a location you just can't get to. Another reason would be if you have limited or unsafe access inside the structure. So if you want to do all the building on the outside, this is one way to be able to do that. And then in some situations, specifically with bridge replacements, you might be dealing with road closures and things like that. So you have limited time when you can close the road to do the work. Doing modular construction allows you to get a lot done without having to close the road. So when we're looking at this, the size of the modules is usually driven by the contractor's lifting equipment capacity and oftentimes the site constraints. So I'm going to show you a couple of case studies that illustrate this, and hopefully that kind of gets you thinking a little bit about how that might work in some of your situations. But as far as I know, this is a pretty novel approach that hasn't been used by too many people, but it's been very successful, and I've been getting very positive feedback when we've used it. This first one is it's actually for a mining project in Utah. This was a cover for an active conveyor to allow access to a new part of the mine where they were going to be doing some new mining. So they had to build an access road to get to the new mining area, and it had to cross this conveyor that was in operation. There was an extremely high cost to disrupt or stop the conveyor operation itself. So high, in fact, that the contract acknowledged that you can't afford to pay what that cost is, and you can't get insurance for it. So that was a driving factor with trying to do a modular construction here. There was a safety issue for one thing to work over an active conveyor, and then also the disruption of service. Addition to that, these structures had to be designed to support a 4 million pound mining shovel, which these structures can easily do. That's something that is routinely done in a lot of mining applications. And this consisted of two different structural geometries. One was roughly a 23 by 11.5 foot single radius arch, and then a 32 by about almost 19-foot rise, a larger dual radius arch, kind of a horseshoe shape. And the reason for the two sizes was that the conveyor had a slope to it at the end, so we needed a taller structure to allow the clearance around the conveyor. The larger structure was pre-assembled in 20 and 25-foot long sections, and the smaller arch was pre-assembled in 40-foot sections up in a laydown area, and then transported about a mile to where the project site was. And then from there, set on the footing and then connected to each other as they go. And all of the work on site around the conveyor is done from the outside of the structure. Individual weights of the modules, in this case, range between about 24,000 and 30,000 pounds. That's a picture of me next to the design vehicle. So when I'm working with people, especially in transportation applications that are, that question whether or not buried bridges can support highway loading, I just kind of laugh that off, because it's between the mining and rail projects I've worked on, that those are pretty easy projects to look at. This is the geometry of the smaller arch. Pretty typical, just a single radius shape, consisted of 3 plates per ring. At this site, they had some additional hardware that had to be attached to accommodate a rail system that they used for doing maintenance on the conveyor, transporting it in and out of the structure. The modular construction actually made that easier, because a lot of that could be done without having it go inside the structure at all. Here's a kind of a plan view, a flattened view of the structure, as if you pushed down the plates and laid them flat. You can see there, this is a 40-foot section here. And then we're going to focus on this joint here. This is the joint between the modules. So these rings over here are all built up on top in a laydown area. These plates lap each other from ring to ring. At the place where this joint is here, the plates are basically butted up to each other. So there's a rolled angle that gets bolted onto the end of each section. And then those angles are mirrored, so that when you set this on the foundation, you bring them together, and then the angles get bolted together, and that closes the gap between the two modules. One of the neat things about flexible buried bridges is that theoretically each ring, when assembled and properly backfilled, can carry the design load. So there is no function of this joint between rings other than just basically holding the plates together and making a continuous structure. So there's no design load that's considered or anything like that in these locations, and that's why these flange connections work here. Down below is a kind of a cross section of what that looks like. So for this one, there was a 4-inch by 4-inch angle, just your typical 4x4 by 1/4-inch angle that was rolled to match the perimeter of the structure, and then it gets bolted on with holes that are already in there, and then bolted onto the structure itself. So at this site, this structure was about 11 or 1,200 feet long. So the contractor actually built a pre-assembly area where he could build a couple of these structures at a time, of these modules at a time. So that's what we're showing here. He has one that's getting ready to be transported, another one that they're working on, finishing up, and then in the background here, they actually pre-built these in 7.5 or 10-foot wide rings, I think, and then pieced them together. So they had a pretty smooth operation working there. On the bottom right, that's a closer up view of what that rolled angle looks like when it's attached to the ends of one of these modules. So the process was they loaded on the truck. They had kind of built a rig on the back of a flatbed where they used these beams to stiffen the bottom of the structure and hold the span. Had it all secured and then transported down deeper into the mine where the site was. And that's what's shown here. So on the truck on the right is that single radius arch, and then on the left, it's a larger one. Lift it off the truck, set it in place. So here you can kind of see how the process works in the mine, and another view of the flange. Michael's getting his hook ready, so I'm going to speed through the rest of this. The second case study is for a project in Alaska. Replacement for a suspension bridge about 100 feet from the bottom of the structure to the top of the road. From a design standpoint, this is going to be backfilled with roller compacted concrete. So from a design standpoint, we only had to design it for about 5 feet of concrete. After that point, the engineer determined that the concrete was going to support all the load. So this is sort of a form work for that. This is a 75-foot span arch, 25-foot rise. Use the same flange connection on the ends. There's some additional reinforcing here because this had skewed ends on it, and they weren't able to do anything on the inside of the structure to support what would normally we would do like a concrete head wall or collar. They weren't able to support the inside of the skew plates to do that. So we used kind of like a cantilever process to support those rings until they got enough concrete on there to carry all the load. This was done in 3 modules. The weights of those are in the bottom here. The middle one here is 20 feet wide. And they set that first because you need that to help hold up the skew plate, the skewed ends. So they pre-assemble that. Well, this is how harsh the site was. They had to do a little bit of cleaning, and the only way to do that was to hang a guy off of a crane. So I don't know if I want to be the guy in the crane or the guy at the end of the hole there. But anyway, same procedure as the Utah project. Build the modules. Between each module, you put the pieces next to each other to make sure they're going to match up. In this case, they did it right up on top next to the existing bridge. So they just picked it up with a crane and lowered it right onto the footing. After it was in place, they installed the beams on the outside to support the skewed ends. We left the ends long or untrimmed here so they could set up their formwork, as they basically slip formed the structure as they placed the roller compacted concrete. So you can see why they didn't want to do any work inside. It's a deep ravine, fast moving water, and really very little space to get any equipment in there. So that's the suspension bridge in the background, and the new structure in front. They've already started backfilling with the concrete here. On the right, they're past that 5-foot limit and basically doing roller compacted concrete the rest of the way up. And it's kind of a tough site to get around in, so we didn't get a good view of the final condition, but there you go. It's about 75 feet from the crown of the structure to the top of the new road. And then I'll just wrap things up with snapshots from this is a transportation project in the eastern part of the country. Hopefully I'll get to do a case study on this one again soon, but this was twin 63-foot span arches for a temporary bridge to use as a bypass during replacement of the existing bridge in the background here. So the contractor built these in 17.5-foot long sections. And because of limited road closures, he would build this during the day, and then they would set the sections at night when they could close the road. The feedback has been very positive. He said it worked very well. Things matched up, and it went a lot faster than anybody was expecting. In the upper right here, you can see what this looks like kind of from the inside of the structure as well. So, and this is a teaser for something that'll be coming through soon from the Short Span Steer Bridge Alliance.